Gravity holds every atom of your body to this planet right now. You have felt it every single moment of your life. And yet, as of today, physics has absolutely no confirmed answer for what gravity actually is at the smallest scale. Every other force in nature has been decoded at the quantum level. Gravity alone remains a mystery. We are going to go from Newton's confession that he had no idea how gravity worked, through Einstein's curved spacetime, through exploding infinities and vibrating strings, and wormholes built from quantum entanglement, all the way to the honest edge of what humanity currently knows. If you enjoy this journey, subscribe and leave a like. It genuinely helps. Prepare yourselves, we begin. Gravity is the most familiar force in the universe, and the least understood. Right now, sitting wherever you are, you feel a pull toward the center of the earth. Your chair pushes back. Your feet press the floor. Every cell in your body is being drawn downward at a constant, steady rate. You have felt this your entire life. You were born into it. You will never escape it. And yet, if you ask the most brilliant physicists alive today to tell you what gravity actually is at its deepest level, they would look at each other and say, honestly, we are still working on that. That answer is not a failure of effort. Thousands of the sharpest minds in human history have worked on this problem. The answer is that gravity turns out to be genuinely profoundly strange. It plays by rules that seem fundamentally incompatible with the rest of physics. And the deeper you push into it, the stranger it gets. Here is the first thing to understand. Physics has a framework called quantum mechanics that describes how everything at the smallest scale works. Particles, forces, fields. It has been tested to extraordinary precision. Every force we know of, electromagnetism, the force that holds atoms together, the force that tears them apart, all of them have been successfully described inside that quantum framework. Physicists found the particles that carry those forces. They built equations that matched experiment after experiment. Gravity has refused every single attempt to bring it inside that framework. Every attempt has broken down. The math produces nonsense. The particles seem undetectable. The theories either contradict each other or predict things too small to ever measure. Gravity sits outside quantum mechanics, like a locked room that physics has been circling for a century. And this is not a minor gap. This is the central open wound in theoretical physics. General relativity, Einstein's theory of gravity, describes the universe at large scales with breathtaking accuracy. Quantum mechanics describes the universe at tiny scales with breathtaking accuracy. When you try to combine them, they destroy each other. The equations collapse. Infinities appear where there should be finite answers. The framework breaks. That gap between the two greatest theories in physics is where this entire journey lives. Here is why you should care about this personally. Gravity is not just a force on your body. Gravity shapes time. Einstein proved that time moves slower near a massive object. The clocks on satellites orbiting Earth tick faster than clocks on the ground. And engineers have to correct for this difference, or your phone's navigation would drift by miles every single day. That correction is real, measurable, and uses Einstein's equations directly. Gravity is woven into the fabric of time itself. So when we say physics cannot fully explain gravity, we are saying physics cannot fully explain time, cannot fully explain what space is made of, cannot explain what happens at the center of a black hole, or at the first instant of the universe's existence, or at the smallest possible scale of reality. All of those questions point back to the same missing piece: quantum gravity. The search for it has produced some of the most beautiful and some of the most bizarre ideas in the history of science. Extra dimensions curled up smaller than anything we can measure. Space-time built from quantum information. Wormholes connecting entangled particles. A universe that may have no fundamental concept of time at all. We are going to walk through every piece of this, carefully, one step at a time. But to understand why quantum gravity is so hard, we first need to understand what gravity looked like before anyone tried to make it quantum. And that story begins with a man who solved gravity's behavior with perfect precision, while openly admitting he had no idea what gravity actually was. Isaac Newton gave the world an equation for gravity in 1687. And it worked so well that engineers still use it today to launch spacecraft. The equation said this: every object with mass pulls on every other object with mass. The strength of that pull depends on the mass of both objects and shrinks as the distance between them grows. Put numbers in, get the right answer out. Every time, the orbits of the planets, the arc of a cannonball, the pull of the ocean into tides, all of it matched. The precision was stunning for its era, and the formula remains accurate enough that it guided the Voyager probes to the outer edges of the solar system over 3 decades of travel. Newton knew his equation was powerful. He also knew something was deeply wrong with it. The problem was called action at a distance. Think about what the equation actually implies. You are standing on Earth. The moon is roughly 240,000 miles away. According to Newton's formula, the Earth and the moon are pulling on each other right now, across that entire gap, with no delay and no physical connection between them. No rope, no signal, no medium carrying the force. Just 2 objects, separated by 250,000 miles of empty space, somehow knowing about each other and pulling toward each other instantaneously. Newton found this idea philosophically absurd. He wrote that no rational person should believe that inanimate matter could act on other matter across a void without any physical mechanism. He said he had framed no hypothesis about the cause. In plain language, I have the math, but I genuinely do not know what is actually happening. That honest confession sat inside physics for over 200 years. The formula kept working. Nobody had a better answer, so scientists used the math and quietly set aside the question of what gravity physically was. Then something subtle started to crack the foundation. In the 1800s, scientists studying electromagnetism, the force behind magnets and electric current, discovered that changes in that force do travel through space. They propagate outward like ripples on a pond. They travel at a specific speed, the speed of light. This suggested that electromagnetic forces are not instantaneous. They spread, they travel, they take time. The idea of a force field, a region of influence that carries information at finite speed, entered physics. Gravity had no such description. Gravity still acted as though it were instantaneous. And when Einstein developed his special theory of relativity in 1905, establishing that nothing, no signal, no influence, no cause of any kind, can travel faster than light, Newton's gravity suddenly faced a deeper problem. An instantaneous force across 240,000 miles of space directly violated the new speed limit of the universe. Something had to give. Either relativity was wrong, or gravity needed a complete reimagining. Einstein spent the next 10 years building that reimagining. He replaced the invisible pull across empty space with something geometrically real, something curved, something you could, at least in principle, picture. The answer he found was so different from Newton's that it changed what physicists thought space and time even were. And yet, even Einstein's beautiful answer, the one that replaced the mystery of pulling with the geometry of curving, would eventually hit its own wall, a wall even harder than Newton's. That wall has a name, and it sits at a scale so small that ordinary intuition completely fails. Einstein's insight did not come from an equation, it came from a thought experiment. He imagined a person inside a closed box, floating in space, far from any planet or star, with no way to look outside. If the box accelerates upward, the person inside gets pressed to the floor. They feel weight. Now imagine the same person standing on the surface of the Earth, feeling gravity press them down. Einstein asked, is there any experiment performed entirely inside that box that could tell the difference between the two situations? His answer was no. Acceleration and gravity feel identical. They are, in some deep physical sense, the same thing. He called this the equivalence principle, and he spent the next decade following its logical consequences all the way into a complete theory of gravity. The theory he built was called general relativity, published in 1915, and its central claim was radical. Gravity is geometry. Space is not just an empty stage where objects perform. Space, combined with time into a single four-dimensional structure called spacetime, has shape. It can curve. It can bend. And the presence of mass is what curves it. A massive object like the Earth warps the spacetime around it, and other objects moving through that warped spacetime follow the curves. What we experience as gravitational pull is the natural path of an object following the curved geometry of spacetime. The classic image is a rubber sheet stretched flat, with a heavy ball placed in the center. The sheet bends downward around the ball. A marble rolled across the sheet curves toward the heavy ball. That curving path is what gravity looks like in Einstein's picture. The marble is not being pulled. It is following the natural contour of the surface it moves through. That image is imperfect, as all analogies are, but the core idea holds. Massive objects warp the geometry of space-time, and that warped geometry dictates how everything else moves. The predictions this theory made were extraordinary. Light itself, traveling through curved space-time near a massive object, should bend. In 1919, astronomers measured starlight bending around the star at the center of our solar system during a solar eclipse, exactly as Einstein predicted. The confirmation made international headlines. Einstein became the most famous scientist alive. General relativity kept winning. It predicted that clocks near massive objects tick slower, and satellite engineers confirm this every day to keep navigation systems accurate. It predicted gravitational waves, ripples spreading outward through space-time when massive objects collide. A century after Einstein wrote his equations, physicists detected those ripples from two colliding black holes a billion light-years away. The signal matched his equations with breathtaking precision. General relativity also predicted its own limits. Deep inside a black hole, at a point called a singularity, the curvature of space-time becomes infinite. The equations produce a meaningless result. Einstein knew this. Physicists since have known it. A singularity is not a physical prediction. It is a sign that the theory has reached its own boundary, a place where it stops being valid and something else must take over. That something else has never been found. General relativity handles the universe at large scales perfectly. But at the smallest scales, at the scale of individual particles and quantum interactions, it fails. And at the interior of a black hole, or at the first fraction of a second after the universe began, those two scales collide directly. To understand why combining them is so difficult, you first need to understand what quantum mechanics actually says about how forces work. Because the quantum story of forces is genuinely unlike anything in daily life. And it starts not with gravity, but with light. Classical physics describes forces as fields. A magnet creates a magnetic field around itself. Another magnet placed nearby feels that field and gets pushed or pulled. Gravity, in Einstein's picture, curves the geometry of space-time. These are continuous, smooth descriptions. Fields extend through space like a fluid, and objects respond to them the way a boat responds to waves. Quantum mechanics has a completely different description of forces. And it is stranger. In quantum field theory, forces are carried by particles. When two electrons repel each other, they do so by exchanging a particle called a photon. The photon flies between them, carries the electromagnetic influence, and the electrons respond. The photon is called a force carrier, or a gauge boson. The electromagnetic force, in the quantum picture, is a constant stream of these exchanges, an invisible traffic of photons passing between charged objects, pushing and pulling them based on the rules of quantum mechanics. This sounds bizarre. You push your hand against a wall and you feel resistance. Are photons flying between your hand and the wall? In a precise technical sense, yes. Trillions upon trillions of virtual photons are exchanged between the electrons in your hand and the electrons in the wall every second. What you feel as solid resistance is the electromagnetic repulsion of those electron clouds, mediated by photon exchanges at quantum scale. The word virtual here is important. These photons are virtual, meaning they exist only as the carriers of an interaction and cannot be individually detected mid-exchange. They are a mathematical tool that describes the probability of the interaction occurring, but the force they produce is completely real and measurable. Every force we know, other than gravity, has been described this way. Electromagnetism has the photon. The strong nuclear force, which holds the nucleus of an atom together, has particles called gluons. The weak nuclear force, responsible for radioactive decay, has three force carriers called W bosons and the Z boson. All of these particles have been detected. The framework that describes them, called the Standard Model of Particle Physics, is one of the most tested and confirmed theories in all of science. Gravity has no place in the standard model. Physicists know what particle would have to carry gravity if it fits this framework. They call it the graviton. They can work out its required properties from the mathematics. It must carry no electric charge. It must travel at the speed of light. It must carry a specific type of spin, twice that of the photon. The math is internally consistent. The graviton fits neatly into the theoretical framework. The problem is not the theory. The problem is reality. The graviton, if it exists, carries a force so extraordinarily weak that detecting a single one may be physically beyond any technology that could ever be built. One calculation showed that a detector the mass of the planet Jupiter, running for a duration longer than the current age of the universe, might catch a handful of gravitons. Maybe. The gravitational force between individual particles is so vanishingly small that its quantum carrier is essentially invisible to experiment. And there is a deeper problem. When physicists try to build the full quantum theory of gravity, following the exact same mathematical procedure that worked for every other force, the math does something uniquely catastrophic. It produces infinities everywhere, and unlike the other forces, there is no known way to remove them. That failure is not a calculation or mistake. It is a signal that something fundamental is missing. And understanding what goes wrong requires understanding what happens when you try to calculate anything. That distance is smaller than a certain absolute limit built into the structure of space itself. Every force carrier ever confirmed shares certain basic features. It can be produced in a laboratory, or at least detected in its effects with high-precision instruments. Photons are detected constantly. Gluons leave traceable signatures in particle accelerators. The W and Z bosons were found at the European Organization for Nuclear Research in the 1980s, exactly where theory predicted they would appear. Force carriers are real, measurable, and confirmable. The graviton sits alone on the other side of a vast experimental chasm. Gravity is, by an almost incomprehensible margin, the weakest force in nature. Pick up a paperclip with a small magnet. You have just demonstrated electromagnetic force, overcoming the gravitational pull of the entire planet Earth, using a magnet small enough to hold in one hand. The electromagnetic force between two electrons is roughly 10 to the power of 42 times stronger than the gravitational force between those same two electrons. Written out, that is a 1 followed by 42 zeros. The gap between gravity and electromagnetism alone is a number larger than the total count of atoms in the observable universe. This weakness is not a minor quirk. It shapes everything about what gravity looks like at the quantum level. Force carriers are exchanged proportionally to the strength of their force. The weaker the force, the rarer the exchange, the quieter the signal. Gravity is so weak that even between subatomic particles, the gravitational interaction is essentially zero for all practical purposes. Two protons inside an atomic nucleus attract each other gravitationally with a force so small that it plays no role whatsoever in their physics. The strong nuclear force holding them together is roughly 100 times stronger than electromagnetism, which is itself 42 orders of magnitude stronger than gravity. Gravity at the quantum scale is a whisper inside a hurricane. This is why detecting a graviton is, by physics estimates, effectively impossible with any conceivable technology. The calculation is blunt. Given the rate at which gravitons would interact with any detector you could build, even one the size of a large planet, the wait time between single graviton events would vastly exceed the age of the universe. Gravity's quantum particle is theoretically real and experimentally unreachable. But the detection problem, severe as it is actually the smaller of the two graviton problems. The bigger one is mathematical. When physicists write down a quantum field theory for the graviton, using the exact procedure that succeeded for electromagnetism and the nuclear forces, the calculations produce results that are infinitely large, an infinite answer for the probability of two gravitons scattering off each other, an infinite answer for the energy of the gravitational vacuum, infinite answers proliferating in every direction. Other quantum field theories produce infinities too, but those infinities can be managed through a technique called renormalization, where you absorb the infinities into measured physical quantities, and the remaining predictions become finite and testable. For quantum gravity, renormalization fails. The infinities multiply without limit. Every time you try to remove one, another one appears. The procedure that rescues every other quantum field theory does nothing for gravity. The math is telling you insistently that you are applying the wrong framework. This is not a problem of insufficient computing power or mathematical creativity. The best mathematical physicists of the 20th and 21st centuries have attacked this problem. The consensus is that gravity at the quantum scale requires a genuinely new kind of theory, one that does not yet fully exist. Understanding why renormalization fails for gravity and why it works for everything else requires going somewhere unsettling, to the smallest scale in nature, the scale where space itself stops making sense. There is a distance so small that the concept of distance itself may stop being meaningful. To reach it, start with something familiar. The nucleus of an atom is roughly 1/10 trillionth of an inch across. That already sits far beyond the threshold of anything visible. A proton inside that nucleus is 100,000 times smaller still. The quarks inside the proton are smaller than any measurement has been able to pin down, somewhere below 1/1000th of 1/1000th of a meter. Keep going smaller, far smaller, 1,000 trillion times smaller than a proton. You arrive at a scale called the Planck length. The Planck length is approximately 1.6 times 10 to the negative 35 meters. For comparison, if a single proton were magnified to the size of the entire observable universe, spanning 93 billion light-years in every direction, the Planck length at that same magnification would be roughly the size of a tree. The gap between the scale of a proton and the Planck length is that extreme. The Planck length is not just another small distance. It is the scale where the two great frameworks of physics predict that all of their usual concepts must break down simultaneously. Here is why. Quantum mechanics tells us that to probe a smaller and smaller distance, you need higher and higher energy. This is a direct consequence of the Heisenberg uncertainty principle. The more precisely you try to locate something, the more energy you need to do it. To probe the scale of a proton, the Large Hadron Collider accelerates particles to immense energies. To probe 1,000 times smaller, you need roughly 1,000 times more energy. To probe down to the Planck length would require concentrating so much energy into so small a space that general relativity predicts that amount of energy would collapse into a black hole. The probe destroys the measurement. The act of looking at that scale creates a gravitational catastrophe. Space-time does not just bend at the Planck scale. Quantum mechanics predicts that at that scale, space-time itself fluctuates wildly, foaming and writhing and twisting in all directions at once. The geometry of space is no longer smooth and well-defined. It is a roiling, probabilistic chaos. Some physicists call this phenomenon quantum foam. At the Planck scale, asking what the distance between 2 points is becomes a question without a clean answer. Space may not come in continuous, divisible chunks the way a ruler suggests. It may be granular, discrete, a minimum unit below which there is simply no further resolution. This is where the conflict between general relativity and quantum mechanics becomes a direct collision. General relativity is built on the assumption that space-time is smooth and continuous at every scale. Quantum mechanics applied to space-time itself predicts that it is violently non-smooth at the Planck scale. Both predictions cannot be correct simultaneously. One, or possibly both, must give way to something deeper. Every serious candidate for a theory of quantum gravity must say something coherent about what happens at the Planck scale. What replaces smooth space-time? What the geometry of reality looks like at that depth? What space and time even mean when you can no longer define a precise distance between 2 points? Two major candidates have spent decades competing to answer that question. They approach it from completely different directions. One of them says the problem is that particles are zero-dimensional points, and the fix is to give them size. The other says the problem is that space-time is assumed to be continuous, and the fix is to make it discrete. The first candidate is the most famous theory in physics that has never been confirmed. String theory began as an attempt to describe the strong nuclear force in the 1960s, failed at that job, was largely abandoned, and then was rediscovered as something far more ambitious. The core idea is simple to state. Every elementary particle in nature, every electron, every quark, every photon, every force carrier, is not a zero-dimensional point. Each one is a tiny loop or strand of energy vibrating at a specific frequency. The different particles are the same underlying string, vibrating in different modes, the way a single guitar string can produce different notes depending on how it vibrates. An electron is one vibration pattern, a quark is another, a photon is another. The size of these strings is predicted to be near the Planck length. They are unimaginably small, far smaller than anything any particle accelerator has ever probed, which is one reason string theory is extraordinarily difficult to test directly. But here is the crucial part for quantum gravity. When physicists mapped out all the possible vibration modes of a closed-loop string, the modes that correspond to different particles and force carriers, they found one particular mode that was unexpected. A massless particle with a spin of 2. They had not put it in by hand. It emerged from the mathematics automatically. A massless spin, 2 particle, is exactly the graviton, the force carrier that quantum gravity requires. String theory predicts the graviton as an unavoidable consequence of its structure. Every consistent version of string theory contains gravity. If string theory is correct, gravity is not bolted on from outside. It is woven into the fabric of the theory from the start. And unlike standard quantum field theory, string theory does not produce the runaway infinities that destroy naive quantum gravity. The strings have a physical size, however small. When you try to calculate a high-energy interaction, the extended nature of the string smooths out the calculation at short distances, removing the infinities that plague point-particle theories. The math stays finite. This was, for many physicists in the 1980s and 90s, enormously compelling. String theory has a further prediction that is deeply strange. The universe must have more than 3 dimensions of space. String theory requires 10 or 11 total dimensions of space-time to be mathematically consistent. Since we clearly experience only 3 dimensions of space and 1 of time, the extra dimensions must be hidden. The standard explanation is that they are compactified, curled up into structures so tiny, near the Planck length in size, that they are invisible to any probe we can currently perform. The shapes of these extra dimensions turn out to matter enormously. Different compactifications produce different physics, different particle masses, different force strengths. String theory does not predict a single universe. It predicts an enormous landscape of possible universes, each corresponding to a different way the extra dimensions can be shaped. Estimates suggest the number of possible configurations is around 10 to the power of 500, a number so large it exceeds any human intuition. This landscape is both a feature and a criticism. Some physicists see it as reflecting the genuine multiplicity of possible physics. Critics argue a theory that encompasses that many possible universes makes no sharp falsifiable predictions about the specific universe we live in. String theory remains the leading candidate in many physics departments worldwide. It has generated extraordinary mathematics. It has led to tools that solved problems in quantum field theory, black hole physics, and condensed matter physics that had nothing directly to do with strings. And it has produced exactly 0 confirmed experimental predictions unique to itself. A rival approach says you do not need strings at all, and it has a radically different picture of what spacetime is made of. Loop quantum gravity starts from a different frustration than string theory. String theorists looked at the problems of quantum gravity and decided the issue was with particles being mathematical points. They extended particles into strings. Loop quantum gravity theorists looked at the same problems and decided the issue was with spacetime being treated as a smooth, continuous background. They decided to quantize spacetime itself. The key move in loop quantum gravity is applying the logic of quantum mechanics directly to the geometry of space. Quantum mechanics tells us that many quantities come in discrete units. Energy does not flow continuously, it comes in packets called quanta. If you apply that same logic to the geometry of spacetime, you arrive at a startling conclusion. Area and volume do not come in continuous amounts either. They come in minimum units. Space is not infinitely divisible. There is a smallest possible chunk of space, roughly at the Planck scale, below which the concept of spatial extent simply does not apply. The mathematical structure that describes this quantized geometry is called a spin network. Picture a vast web of nodes connected by links. Each node represents a quantum of volume, a minimum chunk of space. Each link between nodes represents a quantum of area, the surface shared between two adjacent chunks. Space, at its deepest level, is the network itself. There is no smooth background underneath it. The network is space. This is a profound departure from both Newton and Einstein. Newton assumed space was a fixed flat stage. Einstein said, "Space is dynamic. It curves and bends in response to mass and energy." Loop quantum gravity says space is granular, a discrete network of quanta. And the smooth spacetime of general relativity is what that network looks like when you zoom far enough out, the way a smooth photograph reveals individual pixels, only when you get close enough. When loop quantum gravity evolves forward in time, the spin network changes. Nodes merge, split, reconnect. The theory calls this evolving structure a spin foam, a four-dimensional history of the network's changes through time. The universe in this picture is a spin foam, a constantly changing web of discrete quanta of space-time, churning at the Planck scale, producing the smooth geometry of space and time as a large-scale average. Loop quantum gravity makes a specific and striking prediction about the structure of space. The smallest possible area is approximately 10 to the negative 66 square inches, an area so small that fitting it inside a proton would require dividing the proton into a number of pieces larger than the total count of atoms in the observable universe. Space is discrete, but so profoundly finely grained that we will likely never detect the granularity directly. The theory also makes a striking claim about the Big Bang. In standard general relativity, running time backward toward the origin of the universe leads to a singularity, a point of infinite density where the equations break down. In loop quantum gravity, the discrete nature of space-time prevents infinite compression. The universe does not collapse to a point. Instead, time runs back to a minimum volume, then bounces. Before the Big Bang, in this picture, there was a previous collapsing universe. The Big Bang was a big bounce. This is a testable prediction, at least in principle. Certain patterns in the cosmic microwave background radiation, the oldest light in the universe, might carry the imprint of the pre-bounce era. Current measurements are not yet precise enough to confirm or rule this out, but future telescopes may be able to look. Loop quantum gravity and string theory agree on almost nothing, except that quantum gravity requires something beyond general relativity and quantum mechanics as they currently stand. They disagree on whether extra dimensions exist, whether space-time is continuous or discrete, and whether unifying all forces is even the right goal. But in the last 2 decades, a third set of ideas has appeared that cuts across both approaches and may be pointing at something even deeper. It involves a concept called holography, and what it implies about the nature of space is, by any measure, one of the most radical ideas in the history of physics. In 1993, physicist Gerard Hooft proposed something that sounded more like philosophy than physics. The total amount of information inside any region of space is proportional to the area of its boundary, not its volume. Think about what that means. You have a box. The box has a volume and a surface area. Normally, the more volume you have, the more stuff, the more information you can fit inside. A larger room holds more books, double the volume, store more data. This is intuitive and seemingly obvious. Hooft said it was wrong. The information describing everything inside a volume of space is entirely encoded on the two-dimensional surface surrounding that volume. The interior is, in a deep sense, a projection of the boundary, like a three-dimensional hologram that emerges from a two-dimensional plate. This idea came partly from thinking about black holes and from a calculation that Jacob Bekenstein performed in the early 1970s. Bekenstein asked, how much information can a black hole contain? The answer turned out to scale with the surface area of the black hole's event horizon, the boundary beyond which nothing escapes. Stephen Hawking then showed that black holes have a temperature and slowly radiate energy, and using that radiation, he confirmed the entropy of a black hole scales exactly with its surface area, 1 unit of information per roughly 1 Planck area of boundary surface. This was the first serious hint that in a theory of quantum gravity, the boundary of a region and its interior are not independent. The boundary contains all the information needed to reconstruct the interior. Volume in some sense is redundant, The holographic principle sat as a striking but abstract idea for several years. Then, in 1997, a young physicist named Juan Maldacena made it concrete in a way that sent shockwaves through theoretical physics. Maldacena discovered a precise mathematical equivalence. A quantum gravity theory living in a specific curved space called anti-de Sitter space is exactly equivalent to a quantum field theory with no gravity living on the boundary of that space. These two theories, one with gravity in the bulk and one without gravity on the boundary, describe exactly the same physical reality. In two different mathematical languages, every calculation in one maps to a calculation in the other. This equivalence is called the anti-de Sitter/conformal field theory correspondence, often called the ADS/CFT correspondence. It is the first and, so far, only context in which physicists have a complete, internally consistent mathematical description of quantum gravity. The gravity side of the correspondence behaves quantum mechanically because the boundary theory is fully quantum mechanical. You can translate any question about quantum gravity in the bulk into a question about a conventional quantum field theory on the boundary, and vice versa. The ADS/CFT correspondence is a confirmed mathematical result. The translation between the two theories has been verified in thousands of calculations across several decades. It is the most precisely tested idea in theoretical quantum gravity. The reason it has not solved quantum gravity completely is that anti-de Sitter space has a negative cosmological constant, making it a space that curves inward. The universe we live in has a positive cosmological constant, meaning it curves outward and expands. The correspondence applies directly to anti-de Sitter space. Whether a version of it applies to a universe like ours is an active, unsolved problem. But even as an idealized result, the ADS/CFT correspondence has completely reshaped how physicists think about quantum gravity. It strongly suggests that space-time is not fundamental. The gravitational geometry of the bulk, all those dimensions of space, may be an emergent structure arising from the quantum information of the boundary theory. Space may be something that appears, something that arises from deeper physics, the way temperature appears from the motion of atoms, without being a fundamental ingredient itself. And the place where this idea gets tested most brutally is a region where gravity is so extreme that nothing, not even light, can escape. A black hole forms when matter compresses into a region small enough that the escape velocity exceeds the speed of light. Once the threshold is crossed, space and time inside the boundary restructure themselves such that all paths through space-time lead inward. Escape is not merely difficult, it becomes geometrically impossible. The boundary itself is called the event horizon. It is not a physical surface. No material marks it. An astronaut crossing the event horizon from the outside would feel nothing unusual at the moment of crossing. Tidal forces near a large black hole are gentle enough at the horizon that a human body would be undisturbed. But from that point forward, every path, every future direction through time and space leads deeper inside. At the center, general relativity predicts a singularity, a point of infinite density, a breakdown of all equations. General relativity hands the problem to quantum gravity and says, I cannot describe what is here. Whatever replaces me takes over at this point. This makes black holes the most important natural laboratories for quantum gravity. They are places where the curvature of space-time is not an abstraction. It is extreme, immediate, and real. And they are places where the energy scales involved push directly toward the Planck regime. For most of the 20th century, physicists assumed black holes were simple objects. You fall in, you are gone. The outside universe records your mass, and your electric charge, and your rotation, but nothing else. All other information about what fell in, what it was made of, what quantum state it was in, is lost. This assumption seemed consistent with classical general relativity. Then Hawking changed everything. In 1974, using a combination of quantum mechanics and curved spacetime geometry, Hawking showed that black holes are not entirely black. They glow. They radiate energy slowly, like a warm object radiating heat, through a quantum mechanical process near the event horizon. The temperature of this radiation is extraordinarily low for stellar mass black holes, far below the temperature of the cosmic microwave background, making it unmeasurable, with any current technology. But the prediction is theoretically robust and is accepted by the vast majority of physicists as correct. Hawking radiation carries energy away from the black hole. Over immense timescales, the black hole loses mass and eventually evaporates completely. For a black hole, the mass of the Earth, the evaporation time would exceed the current age of the universe by many orders of magnitude. For a microscopic black hole, it could be quick. But the principle stands: black holes evaporate. And this is where a devastating problem appears. A problem that has driven quantum gravity research for decades and remains, as of today, unsolved. The radiation that Hawking derived appears to be perfectly thermal, random. It carries no information about what fell into the black hole. If you drop a dictionary into a black hole, the radiation coming out carries no trace of the words. If the black hole eventually evaporates completely, and all that remains is this random thermal radiation, then the information in that dictionary has been permanently destroyed. Quantum mechanics says that is impossible. One of the deepest principles of quantum mechanics is that information is conserved. The quantum state of a system always evolves in a way that is, in principle, information cannot be erased from the universe. General relativity and Hawking's calculations say information falls into a black hole and is gone. These two statements cannot both be correct. One of the two greatest frameworks in physics must be giving way in a fundamental way. This is the black hole information paradox, and the tension at its heart gets even sharper, far sharper than most physicists expected. The black hole information paradox sat in the background of theoretical physics for decades as a known puzzle. Most physicists assumed it would eventually be resolved without requiring any drastic change to quantum mechanics or general relativity. Something subtle in the fine structure of Hawking radiation, some quantum effect that would gradually encode information in the outgoing radiation, without being obvious in Hawking's original calculation. Then, in 2012, 4 physicists, Ahmed Almhiri, Donald Maroff, Joseph Polchinski, and James Sully, published a paper that showed the assumed resolution was actually impossible. Their argument is called the firewall paradox. The argument works like this. Quantum mechanics requires that information be conserved. If information escapes the black hole in the Hawking radiation, then the radiation emitted late in the evaporation process must be entangled with the radiation emitted early in the process. That is the only way the information can be transmitted, through quantum entanglement threading through the outgoing radiation. Quantum mechanics also has a rule called monogamy of entanglement. A particle can be maximally entangled with one other particle, and one only. If the late-stage Hawking radiation is entangled with the early-stage radiation outside the black hole, it cannot simultaneously be entangled with the interior of the black hole. General relativity, however, demands that an observer falling smoothly through the event horizon encounter nothing unusual at the crossing. Smooth spacetime at the horizon requires that the quantum fields at the horizon be in their lowest energy state, which requires a specific entanglement between modes of the quantum field just outside and just inside the horizon. These 3 requirements, information conservation, monogamy of entanglement, and smoothness at the horizon, are mutually incompatible. You can satisfy any 2, you cannot satisfy all 3 at once. Something must break. Either information is destroyed, violating quantum mechanics, or the horizon is catastrophically altered, violating general relativity's prediction of a smooth crossing, or something stranger happens that neither theory anticipated. The catastrophic option they identified: if information must be conserved, and entanglement is monogamous, then the entanglement required by general relativity for a smooth horizon must be severed. Severing that entanglement releases energy. An infalling observer, instead of crossing a smooth and visible boundary, slams into a wall of high-energy radiation at the horizon, a firewall. The firewall would end an infalling observer instantly at the horizon, billions of miles before reaching the singularity. General relativity says this should not happen. The firewall paradox says it may be unavoidable if quantum mechanics is correct. No consensus resolution exists. Every proposed solution breaks something. Some physicists accept that information is genuinely destroyed, and quantum mechanics needs modification at extreme scales. Some argue that the firewall is real, and general relativity simply fails at the horizon. Others argue that the resolution involves something so unusual that both theories need to be replaced. The most striking proposed resolution came from a pair of physicists who noticed a connection that had been sitting in the mathematics unnoticed for years. A connection between black holes and a concept that seems on its surface to have nothing to do with them: quantum entanglement and wormholes. What that connection implies about the deep structure of space is something that could genuinely change every framework discussed so far. And whether it is right or wrong, it is already reshaping the language physicists use to talk about the architecture of reality. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a connection so strange that many of their colleagues needed months just to decide whether it was worth taking seriously. Their idea connected two concepts that had always seemed completely unrelated: wormholes, which are theoretical tunnels through the geometry of spacetime, connecting two distant regions, and quantum entanglement, which is the phenomenon where two particles share a quantum state such that measuring one instantly determines the state of the other, regardless of distance. The idea, called the Einstein-Rosen-Einstein-Podolsky-Rosen conjecture, states that these two phenomena are, at some deep level, the same thing. Two entangled particles are connected by a microscopic wormhole. Two entangled black holes are connected by a macroscopic one. Entanglement and spacetime connectivity are different descriptions of one underlying reality. This is radical for a specific reason. Quantum entanglement is a statement about information and quantum states. Wormholes are a statement about the geometry of spacetime. If these are the same thing, then the geometry of spacetime is being generated by quantum information. Space is built from entanglement. The implications extend beyond black holes. If the connectivity of spacetime emerges from patterns of entanglement in an underlying quantum system, then spacetime is an emergent structure. It is not fundamental. It arises from something that has no location, no distance, no geometry, something purely informational and quantum mechanical. The smooth three-dimensional space you experience every day, the space that curves around planets and ripples with gravitational waves, may be a macroscopic average of an enormously complex web of quantum correlations at the Planck scale. Evidence for this view comes from calculations within ADS/CFT. Physicists have shown that entanglement in the boundary quantum field theory is directly associated with geometric connectivity in the bulk gravitational theory. When you take two previously separate boundary theories and entangle them, a wormhole connecting the corresponding bulk geometries appears in the gravity description. Decrease the entanglement and the wormhole narrows. Sever the entanglement completely and the bulk regions disconnect entirely. Space-time geometry responds to entanglement the way temperature responds to the energy of moving atoms. It is a macroscopic property emerging from underlying quantum information. This idea that entanglement builds space is currently a research program. It is a theoretical framework with supporting evidence from specific calculations, a collection of compelling results rather than a complete confirmed theory. The evidence within ADS/CFT is strong. Whether it generalizes to a universe like ours, whether it correctly describes real spacetime outside the idealized anti-de Sitter setting, is an active and unresolved question, but it points towards something. That loop quantum gravity, string theory, and the holographic principle are all gesturing toward from different angles. Space and time may not be the bedrock. They may be built from something deeper. The question of what that something deeper actually is becomes sharpest when you focus on one specific piece of the puzzle that every framework must eventually answer. A piece that sits at the intersection of quantum mechanics and general relativity in the most direct possible way. The problem is time. Pick up any object near you, set it down. You just experience time as a sequence of moments flowing in one direction. Past to future, cause before effect, memory of the past, uncertainty about the future. Time feels like the most fundamental thing in experience, the river you are always swimming in. In physics, time is handled very differently by the two frameworks that quantum gravity must reconcile. And the difference is not a minor technical detail. It is a fundamental incompatibility that cuts to the heart of what a unified theory would even have to look like. In quantum mechanics, time is a fixed external parameter. It is the background against which everything evolves. The quantum state of a system changes as time advances, and the equations describing that change are built on the assumption that time is a continuous external stage. Time in quantum mechanics is not itself a quantum object. You do not apply the uncertainty principle to time the way you do to position or momentum. Time is the frame that holds the picture. In general relativity, time is completely different. Time is part of spacetime, and spacetime is dynamic. It curves, it stretches, it responds to energy and mass. Near a black hole, time slows so dramatically that an outside observer watching someone fall toward the horizon would see them freeze and never arrive. Two clocks at different altitudes tick at different rates. Time is not a fixed external stage. It is a physical entity that participates in the dynamics of gravity. When you try to write a quantum theory of gravity, you need to marry these two pictures. Time cannot be both a fixed background and a dynamical physical participant simultaneously. Something has to give. In the 1960s, physicists Bryce DeWitt and John Wheeler attempted to write the fundamental equation of quantum gravity, combining the structure of quantum mechanics with general relativity. The equation they produced is called the Wheeler-DeWitt equation. It describes the quantum state of the entire universe, the wave function of everything. It contains no time variable at all. The equation is completely static. There is no term expressing change over time. The wave function of the universe, in this equation, simply is. It does not evolve. It does not tick forward. The universe described by the Wheeler-DeWitt equation has no preferred direction from past to future, no external clock against which to measure change. This result is called the problem of time in quantum gravity. If the equation is correct, time as we experience it is not fundamental. It must emerge from something timeless. The river you feel yourself swimming in is a secondary phenomenon, a macroscopic impression arising from correlations between physical systems inside a fundamentally static quantum universe. One approach to this problem, proposed by physicists Don Page and William Wouters in the 1980s, is called the relational interpretation of time. The idea is that time is defined by correlations between physical systems within the universe. A clock inside the universe is entangled with the rest of the universe in a specific way. An observer using that clock experiences a sequence of moments because their quantum state becomes correlated with the clock's state in a time-ordered way. Time is not flowing from outside. It is constructed from the inside, from quantum correlations between subsystems of a universe that is itself timeless. Laboratory experiments in the 2010s confirmed aspects of this relational picture using photon systems, demonstrating that two observers using internal clocks see consistent time evolution, while from an external perspective no time passes. The experiment does not prove the relational view for the whole universe, but it confirms the mathematical consistency of the approach. Time, the thing you trust most, may be an emergent feature of quantum entanglement inside a fundamentally static structure. If that is true, then the question of what gravity is made of reaches all the way down to the question of what time is made of. And the deepest answers may require discarding the framework of space-time itself. Something completely new may be needed, unlike any structure used in either of the theories being unified. And remarkably, recent experiments are beginning to bring this theoretical world into contact with the physical world for the first time. On September 14, 2015, at 5 a.m. Eastern Time, two detectors operated by the Laser Interferometer Gravitational Wave Observatory registered a signal lasting less than 0.2 of a second. The signal was a chirp, a rapid rise in frequency and amplitude, then silence. The two detectors, separated by about 1,900 miles in Louisiana and Washington state, registered the same signal with a 7-millisecond delay between them, consistent with a wave traveling at the speed of light across that distance. The signal matched general relativity's prediction for the gravitational waves produced by two black holes colliding, each roughly 30 times the mass of our star, spiraling toward each other and merging roughly 1.3 billion light-years away. The collision released more energy in gravitational waves in a fraction of a second than all the stars in the observable universe radiate in light during that same fraction of a second. And the amount of that energy that reached Earth moved the mirrors in the detectors by a distance about 1,000th the diameter of a proton. This detection was the first direct confirmation that gravitational waves exist and travel at the speed of light, confirming a core prediction of general relativity that had waited exactly 100 years for proof. It was also confirmation that the geometry of space-time is physical and dynamic in a way that can be measured. For quantum gravity, this matters in several ways. First, gravitational waves traveling at the speed of light constrain alternatives to general relativity. Any quantum gravity theory must reduce to general relativity at large scales in a way that preserves gravitational wave propagation at light speed. Several proposed modifications to general relativity were immediately ruled out by the first detection. Second, the precision of gravitational wave measurements opens a potential window onto quantum gravity signatures. If space-time is discrete at the Planck scale, or if the propagation of gravitational waves is modified by quantum effects at extreme energies, those modifications might accumulate over cosmological distances into measurable deviations. Current detectors are far too coarse to see Planck-scale effects, but the technology is improving rapidly. Third and fourth generation gravitational wave detectors planned for the coming decades will be sensitive enough to probe effects many orders of magnitude smaller than current instruments. Third, gravitational wave observations of merging neutron stars, which are extreme density objects, whose cores may reach densities where quantum gravity effects begin to play a role, could provide indirect constraints on quantum gravity theories. The equation of state of neutron star matter, how it behaves under extreme compression, depends on the quantum structure of matter at nuclear and possibly subnuclear densities. Gravitational wave signals from neutron star mergers carry fingerprints of that equation of state. The detection of gravitational waves transformed the relationship between quantum gravity theory and experiment. For most of the 20th century, quantum gravity was purely theoretical. No experiment could reach remotely close to the energies or scales needed to probe it. Gravitational wave astronomy brought experimental physics into contact with the gravitational sector of nature at a new level of precision. The next generation of experiments goes still further, and some of the most important ones will not involve telescopes or gravitational wave detectors at all. They will involve laboratory tabletop setups so delicate that they can detect the quantum nature of gravity itself, if it exists, using masses small enough to hold in your hand. For most of the history of quantum gravity research, the theoretical and experimental worlds barely touched. Theory was rich, controversial, and self-contained. Experiment had no tools anywhere near sensitive enough to probe Planck-scale physics. The gravitational force between two individual particles is so weak that no laboratory instrument could measure the quantum properties of that force directly. Quantum gravity was physics for theorists, and many physicists assumed it would remain that way for centuries. That assumption is being actively challenged. In 2017, physicists Sogato Bose and Vlatko Vedral, working independently but with overlapping conclusions, alongside Chiara Marletto and Marcus Aspelmeyer's group, proposed an experiment to test whether gravity is quantum mechanical at all, without needing to reach the Planck scale. The key insight was clever. You do not need to detect a graviton to show that gravity is quantum. You just need to show that gravity can create quantum entanglement between two objects. The experiment works in principle like this. Take two small masses, perhaps tiny diamonds or glass spheres, each in a quantum superposition of two different positions simultaneously. Place them close enough that they interact gravitationally but otherwise isolated from all other forces. If gravity is a quantum field, the gravitational interaction between the two masses will entangle their quantum states. After some time, measure the masses and check whether they are entangled. If entanglement is present, it can only have been created by the gravitational interaction. Gravity is quantum. If the masses interact gravitationally but produce no entanglement, it means gravity behaves classically, even when the masses are in quantum superpositions. That would be surprising and would strongly suggest that gravity is fundamentally different from all other forces. This experiment has not yet been performed. The technical challenges are immense. Maintaining two macroscopic masses in quantum superposition is extraordinarily difficult. Quantum superposition, the property that allows a particle to be in two places at once, is fragile. Thermal vibrations, stray electromagnetic fields, air molecules, cosmic rays. All of these destroy quantum superposition almost instantly for large objects. Performing the experiment requires cooling the masses to near absolute zero, isolating them from every possible external disturbance, and conducting the measurement in deep vacuum over a controlled duration. Teams in Europe and North America are currently developing the technology to make this experiment feasible. Estimates suggest a workable version could be within reach within the next 1 to 2 decades, depending on progress in quantum isolation technology. If it succeeds, the result will be a direct observation, not merely an inference, of the quantum nature of gravity. This would be the most important experimental result in fundamental physics since the detection of the Higgs boson in 2012. It would confirm that a graviton, or something functionally equivalent to it, must exist. It would rule out entire classes of theories that treat gravity as a purely classical background. Even more striking, the experiment would also constrain aspects of quantum gravity theory. The rate at which entanglement builds up between the masses depends on the details of the gravitational interaction at the quantum level. Different theoretical models predict slightly different entanglement growth rates. A sufficiently precise measurement could discriminate between them. For the first time, the centuries-old question of what gravity is at its deepest level is moving from the realm of pure mathematics into the domain of laboratory experiment. And if the answer comes back confirming that gravity is quantum mechanical, the implications reach far beyond physics as an academic field. They reach into what it means to understand reality at all. Physics has a list of open problems. Some are large, some are enormous. And then there is quantum gravity. Solving quantum gravity would mean writing down a single consistent framework that correctly describes all of the following: the quantum mechanical behavior of particles at the smallest scales, the structure of space-time at the Planck scale and below, the interior of black holes, the first instant of the universe's existence, and the correct classical limit that reproduces general relativity at large scales and quantum mechanics in the appropriate limit. A complete quantum gravity theory must do all of this simultaneously and make predictions that match every experiment ever performed, plus new experiments not yet conceived. This would be the final unification. Physics has spent 3 centuries discovering that apparently separate phenomena are aspects of the same underlying reality. Electricity and magnetism were unified into electromagnetism. Electromagnetism was unified with the weak nuclear force into the electroweak theory. The electroweak theory and the strong force are partially unified in the standard model. Gravity stands outside all of this. Solving quantum gravity would complete the picture, showing that every phenomenon in nature, from the motion of galaxies to the spin of an electron, emerges from one coherent framework. The practical applications of such knowledge are impossible to predict from where we stand. Every previous unification in physics eventually produced technology that transformed civilization. Maxwell's equations for electromagnetism, written in the 1860s, eventually enabled radio, radar, television, cellular communications, and the entire internet. Quantum mechanics, a theory developed to describe electrons in atoms, produced transistors, lasers, and modern computing. General relativity, considered by many when it was published to be pure abstract theory with no practical application, is now embedded in every navigation system on the planet. A complete theory of quantum gravity would describe physics at the Planck scale. What would follow from that knowledge over decades and centuries is genuinely impossible to predict. History suggests the gap between pure theory and practical application is rarely zero and rarely short. Beyond technology, solving quantum gravity would answer questions about the origin of the universe that current physics cannot reach. The first Planck time after the Big Bang, the interval of roughly 10 to the negative 43 seconds after the origin, is completely inaccessible to both general relativity and quantum mechanics as they stand. A quantum gravity theory that handles the Planck scale would in principle allow physicists to describe what happened at that instant, and potentially to understand whether the Big Bang was a beginning or a transition from something earlier. It would clarify the nature of black hole singularities. Currently, a singularity is the point where physics admits it has run out of answers. A complete quantum gravity theory would replace the singularity with a well-defined physical description. Whatever is happening at the center of a black hole, in that framework, would have a real, calculable answer rather than a breakdown of equations. Perhaps most profoundly, it would answer the question of whether space-time is fundamental, whether space and time are built from something deeper, from quantum information, from entanglement, from a structure that has no location or duration at its core. The answer to that question would reshape what physicists mean by reality itself. Arriving there requires a clear-eyed understanding of where the field stands today. What has been established, what remains speculative, and what is genuinely unknown. This is the honest accounting. Physics journalism often blurs the line between established fact, promising theory, and speculative possibility. On a topic as rich and contested as quantum gravity, that blurring causes real damage to understanding. So here is the actual state of knowledge, as of today. Confirmed by experiment and observation, general relativity correctly describes gravity at all scales accessible to current measurement, from laboratory tests of the inverse square law at fractions of an inch to the dynamics of galaxy clusters spanning millions of light years. Gravitational waves exist, travel at the speed of light, and match Einstein's equations with extraordinary precision. Time dilation near massive objects is real, measured daily, and used in navigation technology. Black holes exist. They have been imaged directly. The quantum mechanical framework, the standard model of particle physics, correctly describes all forces other than gravity, with a precision that is, in some cases, the most accurate prediction in all of science. The black hole entropy formula, relating information content to surface area, is accepted as correct by the vast majority of physicists based on multiple converging theoretical arguments, though it has not been directly measured. Strongly supported theoretical results. Hawking radiation is predicted by combining quantum field theory with curved space-time and is accepted as correct by essentially all working physicists, though it has never been directly detected. The AD/CFT correspondence is a mathematically confirmed duality that provides a consistent framework for quantum gravity in anti-de Sitter space. The holographic principle, that information in a volume is encoded on its boundary, is supported by multiple independent lines of reasoning. Serious theoretical frameworks, without experimental confirmation. String theory remains a consistent mathematical framework that naturally incorporates a graviton and avoids the infinities of naive quantum gravity. It has not made a unique, confirmed experimental prediction. Loop quantum gravity provides a consistent quantization of space-time geometry, with specific predictions about Planck scale discreteness and a potential big bounce cosmology. It has not been confirmed experimentally. The Entanglement Build Space Program, ER equals Einstein-Podolsky-Rosen, and related ideas, is supported by calculations within ADS/CFT, but remains a research program rather than a complete theory. Genuine open mysteries, whether information is preserved in black hole evaporation, remains unresolved. The firewall paradox has no accepted solution. The correct description of physics at and beyond the Planck scale is unknown. Whether time is fundamental or emergent is unknown. Whether our universe has a holographic description analogous to AD/CFT is unknown. Whether quantum gravity effects will ever be measurable in any laboratory is unknown, though the tabletop entanglement experiments offer a realistic near-term possibility. The question that opened this journey, what is gravity made of according to quantum physics, has an honest answer that spans all of these layers. Gravity is described at large scales by the geometry of curved spacetime. At the quantum scale, it almost certainly involves a force carrier called the graviton, though detecting one may be permanently beyond reach. The deeper structure of gravity, the framework in which it unifies with quantum mechanics, is unknown. Every serious candidate for that framework suggests that space-time is not a fundamental ingredient of reality. That space, time, and geometry emerge from something deeper, something quantum, something that may have more to do with information and entanglement than with geometry at all. Physics has never been closer to this answer, and has never been more aware of how far away it still is. The edge of what humanity knows is not a wall. It is a frontier, lit from behind by everything understood so far, and lit from ahead by questions that, once answered, will change what it means to understand the universe you are sitting in right now. The universe began roughly 13.8 billion years ago in a state of extraordinary density and temperature. Everything we can observe, every galaxy, every atom, every photon of light, emerged from an initial condition so compressed that the entire observable universe fit into a region smaller than a proton. General relativity describes the expansion that followed with remarkable accuracy. The cosmic microwave background, the faint glow of ancient light filling the sky in every direction, matches the predictions of standard cosmology to better than 1 part in 100,000. Run the equations backward, and the story gets precise right up to a point. Then it breaks. At roughly 10 to the negative 43 seconds after the beginning, the universe was compressed to the Planck scale. Every physical quantity, temperature, density, spacetime curvature, reached values where quantum gravitational effects are no longer negligible corrections. They dominate. General relativity alone cannot describe that moment. Quantum mechanics alone cannot describe it either. The two together, in their current unreconciled forms, produce nonsense. Everything before that Planck time is simply outside the reach of current physics. The first instant of existence sits in a blind spot built into the foundations of our best theories. This matters for a specific, measurable reason. The universe today contains structures, galaxies arranged in vast filaments and sheets, temperature fluctuations in the ancient light, patterns of matter distributed across billions of light years that trace their origins to quantum fluctuations in the earliest moments. Tiny random variations in energy density, smaller than anything human-built could produce, were stretched to cosmic scales by the rapid expansion of the early universe and seeded everything we see today. Those original quantum fluctuations carry the fingerprint of whatever physics operated at that time. If quantum gravity effects modified the dynamics of the universe during the Planck era, those modifications could leave subtle signatures in the cosmic microwave background and in the large-scale structure of matter. Future measurements of the polarization of the ancient light, the precise pattern of its orientation across the sky, may be sensitive enough to detect those signatures. Whether they would be interpretable as evidence for a specific quantum gravity theory is an active and contested research question. But the theoretical possibility is real. Loop quantum gravity makes a specific prediction here. Its big bounce scenario, in which the current universe emerged from the collapse of a previous universe, rather than from a true beginning, predicts a specific type of correlation in the cosmic microwave background that differs from standard inflationary cosmology. Current measurements are not precise enough to distinguish them. Planned satellite missions in the coming decades may be. String theory's predictions for the early universe depend heavily on the compactification of extra dimensions and on the dynamics of energy fields associated with those dimensions. Different string cosmology models make different predictions that are, in many cases, difficult to distinguish from each other or from non-string alternatives. The predictive situation is less clean. What every quantum gravity framework agrees on is this: the first instant of the universe is a moment where quantum gravity was the only relevant physics. Everything that followed, every structure, every force, every particle, every galaxy, emerged from conditions that quantum gravity shaped. Understanding those conditions is understanding where everything came from. The Big Bang is not just cosmology's origin story. It is quantum gravity's most important test case. And buried in the ancient light spreading across the sky in every direction, there may already be encoded answers to questions physics cannot yet fully ask. Something else, however, was happening in those early moments that deserves its own careful attention. The very forces we take as separate today may have been unified into one at those temperatures, and the path back toward that unification runs directly through quantum gravity. At the energies available in the earliest moments of the universe, the forces of nature behaved differently than they do today. The weak nuclear force and electromagnetism, which appear completely separate at ordinary temperatures, become a single unified electroweak force, above a certain energy threshold. This unification is not a hypothesis. Particle accelerators have confirmed it directly. At energies accessible to the Large Hadron Collider, the mathematical symmetry between the electromagnetic and weak forces is restored, and they behave as one. At ordinary temperatures, a symmetry-breaking process splits them into two distinct forces. the way a single liquid can separate into two distinct phases when cooled. There is strong theoretical evidence, though not yet experimental confirmation, that the strong nuclear force joins the electroweak force at still higher energies, roughly 10 to the 15th times the energy of a proton at rest. This hypothetical unification is called the Grand Unified Theory Scale. Physicists have not reached those energies in any accelerator, and may never do so with any technology built on Earth. But indirect evidence, including the specific way the strengths of the three forces change with energy, suggests they converge toward a single value at that scale. Extrapolate further to energies near the Planck scale. The electromagnetic weak and strong forces, if grand unification is correct, have merged into one. Gravity, by every calculation, is still nowhere near joining them. At the Planck scale, gravity's strength finally becomes comparable to the other forces, but the mathematical framework that would describe a four-way unification does not exist in any complete form. This picture suggests a deep asymmetry. Three of the four forces of nature are already described within a common quantum framework, the Standard Model. They respond to energy in predictable, calculable ways. Their force carriers are all spin-one particles. They all fit inside renormalizable quantum field theories. Gravity alone has spin-2 carriers, resists renormalization, and sits outside the Standard Model entirely. The fact that the other three forces unify progressively with increasing energy strongly suggests that gravity must join them at some energy. The Planck scale is the natural candidate. A complete theory of quantum gravity would therefore be, simultaneously, a theory of complete unification of all forces in nature. String theory's strongest argument rests precisely here. In string theory, all four forces, including gravity, emerge from different vibrational modes of the same underlying strings. The unification is not imposed from outside. It is built into the foundation. Every force is the same object, vibrating differently. The fact that they look separate at low energies is a consequence of the physics of symmetry breaking, the same process that separates electromagnetism from the weak force at everyday temperatures. Loop quantum gravity does not aim at this kind of force unification. It focuses specifically on quantizing spacetime geometry, without necessarily explaining why the other forces have the structure they do. Critics of loop quantum gravity argue this is a significant limitation. Defenders argue that unification of all forces may not be the right goal, that gravity may be fundamentally different from the other forces, for deep reasons that a good theory should explain rather than paper over. The disagreement between these two camps is genuine and unresolved, and it points toward a question that lies beneath both of them. A question about what the other forces are made of when you look at them at the deepest possible level, because the Standard Model, as successful as it is, also has deep internal puzzles, and some of those puzzles may only be solvable in the same framework that solves quantum gravity. You already know gravity is weak. The paperclip and the small magnet illustrated it. But the full depth of gravity's weakness and how strange it is from a theoretical standpoint deserves its own careful attention. In quantum field theory, the masses and interaction strengths of particles are not simply free parameters you plug in by hand and leave alone. Quantum mechanics causes these values to receive corrections from virtual particles constantly appearing and disappearing in the quantum vacuum. For the Higgs boson, the particle responsible for giving other particles their mass, these quantum corrections are calculated to be enormous, pushing the Higgs mass toward the Planck scale, unless the corrections cancel with extraordinary precision. The Higgs boson's measured mass is roughly 125 times the mass of a proton. The Planck mass is roughly 10 to the 19th times the mass of a proton. To get the measured Higgs mass, the quantum corrections must cancel to one part in roughly 10 to the 34th. A cancellation so precise it strains the imagination. This is the hierarchy problem. Physics currently has no natural explanation for why the Higgs mass is so much smaller than the Planck scale. The two most popular proposed solutions, supersymmetry and extra dimensions, are both connected to quantum gravity. Supersymmetry proposes that every particle in nature has a partner particle with different quantum spin properties. For every particle whose quantum corrections push the Higgs mass up, its supersymmetric partner produces a correction that pushes it back down with nearly equal magnitude, naturally producing a small Higgs mass without requiring extraordinary cancellation. Supersymmetry also improves the unification of force strengths at high energies, making grand unification more mathematically precise. And string theory, in its most complete versions, requires supersymmetry. The Large Hadron Collider has searched extensively for supersymmetric partner particles. As of today, none have been found. The energy scales where supersymmetry was most naturally predicted to appear have been largely ruled out. Supersymmetry may exist at higher energies beyond current accelerator reach, or the specific form of supersymmetry most physicists expected may be incorrect, or supersymmetry as a solution to the hierarchy problem may simply be wrong. Extra dimensions offer a different approach. If gravity propagates through more dimensions than the three we experience, its apparent weakness could be explained. The gravitational force is diluted by spreading through those extra dimensions, leaving only a small fraction to affect our three-dimensional world. In this picture, gravity is not intrinsically weaker than the other forces. It only appears weaker because most of it is leaking into dimensions we cannot access. This proposal, associated with the work of Mima Akani Hamed, Sabas Dimopoulos, and Gia Diwali in the late 1990s, makes a striking prediction. Gravity should become much stronger at distances comparable to the size of the extra dimensions. If those extra dimensions are large enough, gravity could show deviations from the standard inverse square law at sub-millimeter distances. Experiments have tested this down to distances of about 50 micrometers and found no deviation. The extra dimensions, if they exist, must be smaller than that. The hierarchy problem remains unsolved. Every proposed solution connects in some way to the physics of extra dimensions, supersymmetry, or both. And both of those concepts are deeply embedded in the landscape of quantum gravity research. Gravity's weakness is not just a curiosity. It may be the most important clue about the deeper structure of space-time and the hidden geometry of nature. And following that clue leads somewhere that upends intuitions about what it even means for a dimension to exist. The idea that space has more than three dimensions sounds like the premise of a science fiction story. It is also one of the most seriously investigated proposals in theoretical physics. The first attempt to use extra dimensions for physics came from Theodor Kaluza in 1921, later refined by Oscar Klein. Kaluza noticed something remarkable. If you write Einstein's equations for gravity in 5 dimensions instead of 4, and then ask what those equations look like when projected down to 4 dimensions, you get two things: Einstein's 4-dimensional gravity plus Maxwell's equations for electromagnetism. Electromagnetism emerges automatically from gravity in 5 dimensions. A single geometric framework produces two forces. Klein suggested the 5th dimension was not large and open like the 3 spatial dimensions we experience. Instead, it was curled into a tiny circle at every point in space. The circumference of that circle would need to be near the Planck length, far too small for any known probe to detect. This compactification explains why we do not experience the 5th dimension directly. Moving a few feet through ordinary space means traversing the extra dimension billions of times over without noticing it, because each circuit is so small. The idea was ahead of its time and largely set aside. String theory revived it dramatically. String theory requires 10 dimensions of spacetime, or 11 in the extended version called M-theory, and the extra 6 or 7 dimensions must be compactified. The shapes into which they are curled are called Calabi-Yau manifolds, geometrically complex, 6-dimensional forms with intricate topology. The specific shape determines the physics of the 4-dimensional world that remains, the masses of particles, the strengths of forces, even the number of particle families. This is both the strength and the weakness of string theory from a predictive standpoint. The richness of possible compactifications means string theory can accommodate almost any pattern of particles and forces. Finding the specific compactification that reproduces our universe's exact particle physics requires identifying one particular geometry among an almost incomprehensibly large set. Extra dimensions also appear in a more recent and observationally relevant context. In Brand-world models, our observable universe is a 3-dimensional space called the bulk. Ordinary matter and forces are confined to the brain. Gravity alone can propagate through the bulk, which is why it appears so weak on our brain. Its force lines spread into dimensions we cannot access. This picture has a specific experimental signature. If gravity propagates into extra dimensions, Its strength should deviate from the standard inverse square law at short distances. Precision measurements of gravity at distances below 1 millimeter are extraordinarily difficult. Current experiments have constrained extra dimensions in the model-dependent range, but there remains unexplored territory at smaller scales. Perhaps most dramatically, if extra dimensions exist and are accessible to gravity, small microscopic black holes could form at high-energy collisions. Their properties would differ from standard four-dimensional black holes in ways that might be detectable at particle accelerators. The Large Hadron Collider searched for these. No evidence was found in the mass range where the simplest models predicted them. This places constraints on specific brane-world scenarios, but does not rule out extra dimensions in general. The landscape of extra-dimensional physics remains wide open. The dimensions may be too small to probe with current technology, or they may manifest at energy scales just beyond current reach. Or they may not exist at all, and the compactification picture may be a mathematical feature of string theory that does not correspond to physical reality. What remains certain is that addressing gravity at the quantum level forces the question of spatial dimensionality to become a live, physical question rather than a philosophical one. The number of dimensions in nature is not obviously fixed at 3 + 1. It may be determined by dynamics. And there is another candidate for the deepest structure of reality that does not require any extra dimensions at all. One that says the problem is not the number of dimensions, but the concept of a background space-time entirely. Strip away everything continuous from space-time. Remove the smooth manifold. Remove even the concept of distance. Ask what is left when you take away everything that might be an approximation. What remains, according to the causal set approach to quantum gravity, is order. The fundamental structure of the universe is a collection of events, each one a point in history, related by a single rule. Which events can causally influence which other events? Event A can influence event B, if and only if a signal traveling at or below the speed of light can reach B from A. That causal ordering is the only structure that survives. Everything else, distance, duration, geometry, dimensionality, is emergent. It arises from the pattern of causal relations in the same way that temperature arises from atomic motion. The continuous spacetime of general relativity is an approximation of a fundamentally discrete set of causally related events, in the same way that a smooth surface is an approximation of a discrete arrangement of atoms. The causal set approach was proposed by Raphael Sorkin and collaborators in the 1980s and has grown steadily as a research program. It has several appealing features. It is genuinely background independent. There is no fixed space-time arena that the physics takes place in. The space-time arena is itself what is being described. It is Lorentz invariant at the fundamental level, meaning it does not pick a preferred direction in space-time, unlike some lattice-based approaches to quantum gravity that break Lorentz symmetry. And it is radically minimal, making no assumptions beyond causal ordering. The approach has produced at least one genuine predictive success. In the 1990s, causal set theorists estimated the value of the cosmological constant, the parameter describing the energy density of the quantum vacuum that drives the accelerating expansion of the universe. Their estimate, based on causal set reasoning about quantum fluctuations of the discrete events, matched the observed value of the cosmological constant to within an order of magnitude. The cosmological constant has a measured value that standard quantum field theory overestimates by a factor of roughly 10 to the 120. The causal set estimate, while rough, came far closer than any other approach. This remains controversial. The causal set estimate involves assumptions about the statistical behavior of the discrete events that are not uniquely determined. Other researchers have questioned whether the agreement was a genuine prediction or a result of fitting assumptions. But it stands as one of the very few instances where a quantum gravity approach produced a prior estimate of a measured cosmological quantity. The causal set program also makes predictions about Lorentz symmetry violation that are, in principle, testable with high-precision astronomical measurements. If space-time is discrete, photons of different energies traveling across cosmological distances might arrive at slightly different times, an effect that accumulates over billions of light-years, even if the underlying discreteness is at the Planck scale. Gamma-ray burst observations have placed constraints on this effect. Current data is consistent with Lorentz symmetry at the Planck scale, but the constraints are not yet tight enough to fully probe the causal set predictions. What is intellectually striking about the causal set approach is its answer to the question of what spacetime is made of. The answer is events and the order between them, nothing more. No continuous manifold, no metric, no coordinates. Just a web of causal relationships from which geometry grows the way a city's layout grows from roads. Whether causal sets are the correct description is unknown, but the philosophical move they make, replacing continuous geometry with discrete order, captures something that many quantum gravity researchers across different approaches increasingly believe. That space-time, as Einstein described it, is an approximation, something that works beautifully at large scales and breaks completely at small ones. Something built from something else. The hunt for that something else has been one of the defining projects of theoretical physics for half a century. And some of the most surprising progress has come from an unexpected direction. From thinking about what happens when you try to describe reality from inside a black hole versus from outside it. One of the most unsettling implications of combining quantum mechanics with gravity is that what is real may depend on who is asking. In ordinary quantum mechanics, the measurement problem already suggests something strange about observation. A quantum system exists in a superposition of possible states until a measurement forces it into one definite state. The precise nature of this process, what counts as a measurement, what triggers the collapse, is one of the deepest unresolved problems in the foundations of quantum theory. Different interpretations of quantum mechanics give very different answers, and experiments have not definitively settled the question. When gravity enters, the problem deepens. Consider an observer falling into a black hole and an observer watching from safely outside. These two observers describe the same physical process in ways that are, at face value, contradictory. The outside observer watches the infalling observer approach the event horizon and sees them slow down, their signals becoming increasingly redshifted and time-dilated, asymptotically approaching but never crossing the horizon. The infalling observer, from their own perspective, crosses the horizon in finite proper time and continues inward without any singular experience at the boundary itself. These two descriptions are consistent in standard general relativity, each valid in its own reference frame. But quantum mechanics introduces a new conflict. The outside observer, once Hawking radiation is included, sees the infalling observer's information encoded in the outgoing radiation. The infalling observer sees themselves passing smoothly through an unremarkable horizon. Both cannot be simultaneously and completely true without violating the principle that information cannot be copied, called the no-cloning theorem of quantum mechanics. Black hole complementarity, proposed by Leonard Susskind, Lars Thorlacius, and John Uglum in the 1990s, proposes a resolution. The two descriptions, inside and outside, cannot be compared by any single observer. The outside observer can see the radiation encoding the infalling information, or they can dive in and see the infalling observer intact inside, but they cannot do both simultaneously and bring the results together. The information is not duplicated in any operationally accessible sense. This proposal restores consistency, but at a striking philosophical price. The complete description of a physical process now depends irreducibly on the reference frame of the observer. There is no single God's eye view that encompasses both inside and outside simultaneously. The universe does not have a single complete description. It has a collection of observer-dependent descriptions that are mutually consistent, but cannot be globally combined. This observer dependence is not an epistemic limitation, a matter of simply not having access to information. It appears to be a fundamental feature of the physics. In quantum gravity, the question of what is real may have no answer that transcends all observers. This connects to broader ideas in the foundations of quantum mechanics about whether the wave function represents physical reality or only an observer's information about physical reality. In quantum gravity, these foundational questions become physically sharp. The observer is part of the gravitational system. The geometry of spacetime is part of what the wave function describes. Separating the observer from the observed becomes at the deepest level impossible. The implications for our understanding of reality are profound, and they become sharpest in a context where the observer themselves is described by quantum gravity. In the very early universe, where there was no exterior classical observer, and quantum gravity governed everything. What does it mean to apply quantum mechanics to the universe as a whole? This question leads to one of the strangest and most disputed frontiers in all of physics. Quantum mechanics describes systems using a wave function, a mathematical object that encodes the probabilities of all possible states the system could be found in upon measurement. The wave function of an electron describes the probability distribution of its position, momentum, and spin. The wave function evolves smoothly over time according to the Schrödinger equation, until a measurement is made. Apply this framework to the universe itself, and problems appear immediately. The universe, by definition, contains everything. There is no external observer positioned outside the universe to make measurements. There is no external clock against which to define the time evolution of the universal wave function. There is no boundary between the quantum system and the measuring apparatus when the system is all of reality. The standard structure of quantum mechanics, which assumes a division between the quantum system being measured and the classical apparatus doing the measuring, simply does not apply. This is the measurement problem at cosmological scale. It forced physicists to develop interpretations of quantum mechanics that do not depend on external measurement, and the two most prominent of these, the many worlds interpretation and the consistent histories framework, have direct implications for how quantum gravity is formulated. In the many worlds interpretation, the universal wave function never collapses. Every quantum event that appears to have a definite outcome in our experience is actually a branching. All outcomes occur simultaneously in different branches of the wave function. What we experience as a definite outcome is our branch of reality, one among an enormous number of coexisting branches. The appearance of collapse is a consequence of entanglement between the measuring system and the environment, a process called decoherence. In quantum gravity, the many worlds interpretation implies that the wave function of the universe is a superposition of different spacetime geometries. Different histories of the universe, different ways the geometry of spacetime evolved from the initial conditions, all coexist in the universal wave function. What we experience as the unique history of our universe is one branch among many. Stephen Hawking and James Hartle proposed in 1983 that the wave function of the universe could be computed directly, using a procedure borrowed from the path integral formulation of quantum mechanics, but applied to space-time geometries. Their proposal, called the no-boundary proposal or the Hartle-Hawking state, says the universe has no initial boundary in time. Instead of a sharp beginning at the Big Bang, the universe's quantum history has a smooth, rounded geometry in imaginary time, the way the surface of a sphere has no edge. Time as an emergent concept begins gradually rather than sharply. The Hartle-Hawking state makes predictions about the initial conditions of the universe that in principle constrain the properties of the cosmic microwave background. Different versions of the proposal predict different probabilities for different initial conditions. Comparing these predictions to measurements is technically difficult and theoretically contested, but the program represents a genuine attempt to apply quantum gravity to the question of cosmic origins. What makes the wave function of the universe philosophically distinctive is what it implies about possibility. In standard physics, the universe had some initial state and evolved deterministically or probabilistically from there. In quantum cosmology, the universe's initial state is itself a quantum amplitude, a superposition of all possible beginning conditions weighted by their probability. The universe does not simply have a history, it has a quantum amplitude for every possible history simultaneously. Whether this is the correct description of reality at the deepest level, no one knows. It is the framework that follows when you take quantum mechanics seriously and apply it without restriction. And it raises a question that connects back to the structure of gravity in a way that has not yet been fully explored. If the geometry of spacetime is described by a wave function, and that wave function can be in a superposition, then what does it mean for two objects to have a definite distance between them? What does it mean for spacetime to have a definite shape? The answer may require completely reformulating what we mean by geometry itself. In ordinary quantum mechanics, a particle can be in two places simultaneously, until measured. The two positions exist as a superposition, interfering with each other, in ways that produce measurable effects like the double slit pattern. This is confirmed, tested, and applied in technology every day. Now apply the same logic to spacetime geometry. In quantum gravity, the geometry of space is a dynamical physical quantity. It responds to energy, it evolves, it has measurable values. Quantum mechanics applied to any dynamical quantity produces superpositions and interference. So the geometry of space-time should be capable of being in a superposition. Two different geometries, two different space-times existing simultaneously as a quantum superposition. A spatial distance that is genuinely indefinite, not because of ignorance but because of quantum mechanics. A space-time curvature that is in multiple states at once. This is deeply strange to contemplate, because space-time geometry is the arena in which we describe everything else. If the arena itself is in a superposition, what does it mean to say a particle is at a definite location? Locations are defined relative to space-time. If space-time is indefinite, location may be fundamentally indefinite in a way that goes beyond ordinary quantum uncertainty. This issue is not merely philosophical. It creates concrete technical problems for writing down a quantum gravity theory. Ordinary quantum field theory, including the Standard Model, is formulated on a fixed classical background spacetime. The geometry of the arena is assumed to be definite, smooth, and unperturbed by the quantum fields living in it. This assumption fails in quantum gravity. The geometry and the fields must be quantized simultaneously, and they interact with each other in ways that make the combined quantum problem immensely more difficult than either alone. One approach to handling this is the path integral over geometries. Instead of selecting a single spacetime to use as a background, you sum over all possible spacetime geometries simultaneously, weighted by their quantum mechanical probability amplitude. The result is a quantum amplitude for the outcome of interest, averaged over all possible spatial and temporal configurations of the universe between initial and final states. Every possible history of spacetime geometry contributes, the way every possible path of a particle contributes, in Feynman's path integral formulation of quantum mechanics. This procedure is mathematically well defined in specific settings, including the Euclidean quantum gravity program associated with Hawking and his collaborators in the 1970s and 80s. But making it fully rigorous, finite, and physically predictive in general remains unsolved. Causal dynamical triangulations, a modern approach developed by Renate Lal, Jan Amjohn, and Jerzy Jerkiewicz, implements the sum over geometries numerically. The idea is to build space-time out of tiny simplicial building blocks, four-dimensional analogues of triangles, and perform the sum over all possible ways those building blocks can be assembled, subject to the constraint that causality is preserved. Running this sum on computers, the researchers found something remarkable. The large-scale geometry that emerges from the sum is four-dimensional and resembles de Sitter space, the geometry of our expanding universe. No four-dimensionality was imposed by hand. It emerged from the quantum sum over all geometries. This is a hint, not a proof. The result shows that certain quantum gravity approaches produce recognizable space-time as an emergent phenomenon from quantum averaging. But causal dynamical triangulations has not yet been shown to produce the correct matter content or force structure of our universe. It is an approach to the gravitational sector only. The superposition of spacetimes is real physics, not metaphor. And testing it, actually measuring the quantum mechanical behavior of spacetime geometry in a laboratory, is what the tabletop quantum gravity experiments are ultimately aiming toward. If two masses held in quantum superposition of positions can become gravitationally entangled, the spacetime geometry between them has in some sense been in a superposition during the experiment. Whether that interpretation is exactly correct depends on which quantum gravity framework is right. But the experiment probes the question directly. Reaching the Planck scale with a particle accelerator is impossible with any foreseeable technology. The Planck energy is roughly 10 billion times the energy of the protons colliding in the Large Hadron Collider. Building an accelerator capable of reaching it would require a machine on the scale of a galaxy. This is not a challenge of engineering. It is a challenge of fundamental economics and physics simultaneously. But the Planck scale is not the only place where quantum effects and curved spacetime interact. There is a class of physical systems called analog gravity systems, where the mathematics of curved spacetime physics appears in an entirely different physical context, one that can be built and studied in a laboratory. The concept was introduced by William Unruh in 1981. Unruh showed that sound waves moving through a fluid with a background flow can behave mathematically exactly like light waves moving through curved space-time. Specifically, a region of the fluid where the flow velocity exceeds the speed of sound acts as an acoustic analog of a black hole's event horizon. Sound cannot escape from that region, just as light cannot escape from a gravitational event horizon. The analogy is not merely poetic. The equations governing the sound waves in the moving fluid and the equations governing light waves near a black hole are mathematically identical. Unruh then derived an analog of Hawking radiation for these acoustic black holes. Quantum fluctuations in the fluid should produce pairs of sound quanta, with one trapped inside the acoustic horizon and one escaping, carrying thermal energy away from the region, exactly as Hawking radiation works for gravitational black holes. This acoustic Hawking radiation is called the Unruh-Hawking effect in analog systems. In 2019, Jeff Steinhauer at the Technion in Israel reported the observation of this analog Hawking radiation in a Bose-Einstein condensate, an ultra-cold fluid of atoms, cooled to near absolute zero where quantum effects dominate. The condensate was set up with a region of supersonic flow acting as an acoustic horizon. Measurements revealed thermal correlations between quantum fluctuations on opposite sides of the horizon, consistent with the Hawking mechanism. The results have been debated and examined carefully, with most of the community concluding they represent a genuine analog of Hawking radiation. This does not confirm that real black holes emit Hawking radiation. The physics of the fluid is very different from the physics of spacetime, but it does confirm that the mathematical mechanism underlying Hawking's derivation is physically real and produces measurable effects when the right mathematical structure is present. It validates the theoretical machinery in a setting where the experiment can actually be done. Analog gravity experiments are also being used to study the behavior of fields near horizons more generally, to probe the Unruh effect, which predicts that an accelerating observer should see a thermal bath of particles in a vacuum that a stationary observer sees as empty, and to explore aspects of the information problem in analogy with acoustic systems. None of these experiments prove or disprove specific quantum gravity theories directly. They test the reliability of the mathematical tools those theories use. The analog gravity program represents a kind of experimental philosophy for quantum gravity. You cannot go to the Planck scale, but you can go to systems that share the relevant mathematical structure and test whether that structure behaves as predicted. The results so far support the theoretical frameworks rather than undermining them, and they point toward a real possibility if the mathematical structure of quantum gravity, including holography and the emergence of space-time from quantum information, can be realized in laboratory condensed matter systems. Those systems become direct experimental windows into the behavior of quantum gravity, at least within the scope of the shared mathematics. That opens a door that was previously thought permanently closed. This connection sounds improbable. Condensed matter physics studies the behavior of large collections of atoms, solids, liquids, superconductors, magnetic materials. It is the physics of things you can touch. Quantum gravity studies the structure of space-time at the Planck scale. The gap between these two fields in both energy scale and subject matter appears total. They are deeply connected. The connection runs through the ADS/CFT correspondence and its extensions. The boundary theory in ADS/CFT, the quantum field theory without gravity that encodes everything happening in the gravitational bulk, has a mathematical structure very similar to certain condensed matter systems. Specifically, it shares features with strongly correlated electron systems, materials where electrons interact so intensely that the standard perturbative methods of quantum field theory fail completely. And the system exhibits collective behavior that is extremely difficult to calculate. Physicists discovered that ADS/CFT, a tool developed to understand quantum gravity, provides powerful new methods for calculating the properties of these strongly correlated materials. The gravitational bulk description offers a way to compute things that are nearly impossible to compute directly in the boundary quantum field theory. High-temperature superconductivity, which occurs in certain copper oxide materials at temperatures far above what standard theory predicts, involves strongly correlated electron behavior that has resisted full theoretical description for decades. ADS/CFT-inspired methods have produced calculations that match experimental observations in these materials more accurately than previous approaches. This is extraordinary. A framework developed to understand the interior of black holes has become a practical tool for understanding exotic behavior in materials on laboratory benchtops. The relationship goes both ways. Condensed matter physics has a concept called emergence. Macroscopic phenomena like electrical resistance, magnetism, or superconductivity are not present in individual atoms. They arise from collective behavior of enormous numbers of atoms. The emergent phenomena have properties and symmetries that are not obviously present in the microscopic constituents. This is precisely the kind of thing quantum gravity theorists believe is happening with spacetime. Macroscopic geometry emerging from microscopic quantum constituents that have no geometric properties individually. Condensed matter physicists have spent decades developing precise theoretical frameworks for understanding emergence in quantum systems. The renormalization group, the mathematical tool for understanding how physics changes as you zoom in or zoom out, was developed largely in the context of condensed matter phase transitions. It turns out to be deeply relevant to understanding how the large-scale smooth spacetime of general relativity emerges from a discrete quantum description at the Planck scale. Tensor networks, a class of mathematical objects developed in condensed matter physics to efficiently describe strongly entangled quantum systems, have been proposed as a model for the structure of spacetime itself. The multi-scale entanglement renormalization ansatz, a specific tensor network architecture, has a geometry that naturally reproduces features of anti-de Sitter space. The spatial structure of the tensor network encodes the same entanglement patterns as the gravitational bulk. This is a concrete realization of the idea that spacetime geometry emerges from quantum entanglement. The tensor network is the quantum information structure. The anti-de Sitter geometry is what emerges from it. The connection is mathematically precise, not merely analogical. None of this proves that the real universe works this way. These are exact results within specific mathematical frameworks, not confirmations of a physical theory of quantum gravity. But the convergence of quantum gravity, quantum information, and condensed matter physics around the same mathematical structures is one of the most striking developments in theoretical physics of the last 2 decades. Something important is being discovered in this overlap. The full shape of what it is has not yet appeared. 30 years ago, the overlap between quantum information theory and fundamental physics was minimal. Quantum information was a young field concerned with what kinds of computations are possible using quantum mechanical systems. High-energy physics and quantum gravity were largely separate cultures, with different methods, different languages, and different priorities. Today, quantum information concepts sit at the center of the most active research in quantum gravity. The language of entanglement, quantum error correction, tensor networks, and information complexity has become the primary language in which progress on quantum gravity is being expressed. The most striking example is quantum error correction and its role in the structure of holography. Quantum error correction is a technique for encoding quantum information across multiple physical systems in such a way that errors affecting individual systems can be detected and corrected without destroying the information. It was developed for the practical purpose of making quantum computers reliable. In 2015, Ahmed Almhiri, Shidong, and Daniel Harlow showed that the ADS/CFT correspondence has the mathematical structure of a quantum error-correcting code. The information describing a region of the bulk space-time is encoded redundantly across multiple regions of the boundary theory, in exactly the pattern characteristic of quantum error correction. A local piece of the boundary can be corrupted or lost, and the bulk information is still reconstructible from the remaining parts of the boundary. This has a profound implication for the black hole information paradox. If the bulk space-time is an error-corrected encoding of boundary quantum information, then information falling into a black hole is not locally destroyed. It is encoded non-locally across the boundary quantum state, spread across the entire system in a way that is robust against local perturbations. The information is safe in the error-correcting code, even as it disappears locally from the bulk perspective. This framework also illuminates the firewall paradox. The smoothness of the horizon in the bulk description corresponds to a specific pattern of entanglement in the boundary code. What looks locally like empty smooth space at the horizon is globally a highly complex quantum state on the boundary. The firewall paradox becomes, in this language, a question about whether that complex quantum state can be locally decoded or only globally. A second quantum information concept that has become central is computational complexity. The quantum complexity of a state measures how many quantum operations are required to prepare it from a simple reference state. John Preskill, Patrick Hayden, and others showed that the complexity of the boundary quantum state in AD/CFT corresponds to geometric quantities in the bulk spacetime. One proposal, called complexity equals volume, says the quantum complexity of the boundary state equals the volume of a certain maximal spatial slice in the bulk. Another, called complexity equals action, relates it to a gravitational action integral. These proposals are not yet proven in full generality, but they suggest that the geometry of spacetime, specifically the depth and volume of spacetime regions, may be a direct physical manifestation of computational complexity in the underlying quantum theory. Space is how complex the quantum state is. This is another version of the idea that spacetime is emergent. The geometry emerges from quantum information. The metric, the mathematical object encoding distances and shapes in spacetime, may be a macroscopic reading of quantum entanglement patterns and computational complexity. If this is right, then the question of what gravity is made of has an answer that would have been unrecognizable to Newton and startling even to Einstein. Gravity is the macroscopic shape of quantum information. The curvature of spacetime near a massive object is a pattern of quantum complexity and entanglement in the underlying microscopic structure. Whether this is exactly right or approximately right or wrong in an instructive way, no one yet knows. But the convergence of quantum information and quantum gravity around this idea is real, productive, and accelerating. The universe is expanding. That has been known since the 1920s. What was discovered in 1998, to the complete surprise of the physics community, is that the expansion is accelerating. Galaxies are not just moving apart. They are moving apart faster and faster. Something is pushing them, filling the vacuum of space with an energy that drives outward expansion. This something is called dark energy. Its measured value, the cosmological constant, is tiny by the standards of particle physics. It contributes a small but persistent energy density to every cubic inch of empty space, amounting to something equivalent to a few protons worth of energy per cubic yard of space across the entire universe. Quantum field theory predicts this quantity from first principles. Every quantum field, including the electromagnetic field, has zero-point energy, a minimum energy it retains even in its ground state, because quantum mechanics forbids any quantity from being perfectly at rest. Sum these zero-point energies across all quantum fields, and you get a predicted value for the energy density of the vacuum. The prediction and the measurement disagree by a factor of roughly 10 to the 120. The theoretical prediction overshoots the observed value by 120 orders of magnitude, a 1 followed by 120 zeros. This is the largest discrepancy between a theoretical prediction and a measured value in all of science. It is called the cosmological constant problem, and it is widely considered the single most embarrassing unresolved problem in theoretical physics. Something is cancelling the enormous vacuum energy contributions predicted by quantum field theory, reducing the effective cosmological constant to an almost but not quite zero value. The cancellation must be precise to 120 decimal places. No known physical mechanism produces this cancellation naturally. Quantum gravity is expected to be relevant here, because the cosmological constant is a property of the quantum vacuum, and the quantum vacuum is itself affected by gravity. A complete theory of quantum gravity would presumably predict the value of the cosmological constant from first principles, or at least explain why the cancellation is so precise. String theory's approach through the landscape of possible vacua provides a potential anthropic explanation. Among the roughly 10 to the 500 possible compactifications of string theory, some tiny fraction would produce a small but non-zero cosmological constant. If only those vacua produce stable universes capable of forming galaxies, stars, and the conditions necessary for observers, then observers will always find themselves in a universe with a small cosmological constant, simply because that is the only kind of universe in which observers can exist. The measured value is small, because large values produce universes incompatible with our existence. Many physicists find this reasoning unsatisfying. It predicts that the cosmological constant will be small, but does not predict its specific value. It is an explanation that works by invoking the selection effect of observers, which is difficult to test or falsify. Whether it is physics or philosophy depends on whom you ask, and the disagreement is genuine and unresolved. Loop quantum gravity, causal set theory, and other approaches each have things to say about the cosmological constant, but none has produced a convincing derivation of its observed value from fundamental principles. The cosmological constant problem remains fully open. It is also a reminder that quantum gravity is not purely an abstract theoretical puzzle. It has a direct observational consequence that shapes the large-scale fate of the universe. Dark energy will continue to drive the accelerating expansion of the universe for billions of years into the future. Whether the expansion continues forever, or whether quantum gravity effects at some future point modify or reverse it, depends on questions that physics cannot currently answer. The universe's destiny and the structure of space-time at the Planck scale are connected by the same missing framework. Black holes evaporate. Hawking radiation slowly drains their mass over immense timescales. For a black hole with the mass of our star, the evaporation time is longer than the current age of the universe, by a factor so large it would require more digits to write than there are atoms in the observable universe. For a tiny microscopic black hole with the mass of a mountain compressed to a point, the evaporation would be rapid, ending in a burst of high-energy radiation. The question of what happens in the final moments of evaporation is where quantum gravity is most directly forced to produce an answer. As the black hole shrinks, its temperature rises. Hawking's formula says the temperature of the radiation is inversely proportional to the black hole's mass. A smaller black hole runs hotter. Near the end, as the mass approaches the Planck mass, the temperature approaches the Planck temperature, an energy scale so extreme that quantum gravitational effects completely dominate. The final evaporation is entirely a quantum gravity event. Standard quantum field theory on curved spacetime, the framework Hawking used to derive his radiation formula, breaks down precisely at this point. It cannot describe the final stages. It cannot say what, if anything, remains after the last Planck mass remnant evaporates. It cannot say whether the information that fell in comes out, stays locked in a remnant, or is genuinely destroyed. Three scenarios exist in the literature, each with serious proponents and serious problems. Information comes out in the radiation. If quantum mechanics is exactly right, and information is conserved, the information that fell into the black hole must escape in the Hawking radiation, encoded in subtle quantum correlations in the outgoing thermal-looking radiation that Hawking's calculation cannot resolve. This is the mainstream view today, supported by the ADS/CFT correspondence, by the page curve argument, and by most current quantum gravity research. The problem is that no one can give a complete, explicit description of how information escapes while the black hole geometry looks smooth and nothing dramatic appears to happen at the horizon. Information is permanently destroyed. A small minority of physicists maintain that black holes genuinely destroy information, and quantum mechanics must be modified at extreme scales to allow this. The modification required would be drastic, affecting the foundations of quantum mechanics rather than just quantum gravity. Experimental constraints on modifications to quantum mechanics are extraordinarily tight, making this position difficult to maintain without predicting other observable effects. A Planck-scale remnant retains the information indefinitely. Perhaps the black hole does not evaporate completely. Perhaps evaporation halts at the Planck mass, and a stable or very long-lived remnant remains, carrying all the information of everything that ever fell in. This scenario has a serious problem. A Planck mass object carrying an arbitrary amount of information would have an arbitrary number of internal states accessible at very low energies, violating thermodynamic principles in a way that causes other theoretical inconsistencies. The current consensus, fragile and incomplete as it is, leans toward information escaping in the radiation. The page curve, a prediction of how the entanglement entropy of the Hawking radiation should evolve over the lifetime of the black hole, if information is conserved, has been derived in certain idealized quantum gravity frameworks using the Ryu-Takayanagi formula. from AD/CFT and related techniques. The derivation provides a strong argument that information is preserved, encoded non-locally in the radiation, without requiring a firewall or a dramatic departure from smooth horizon physics. But the derivation is in an idealized setting. It does not give a microscopic step-by-step description of how information escapes. That description, the explicit mechanism, remains unknown. It is one of the central missing pieces in quantum gravity. The answer, when it comes, will require a complete quantum gravity theory to express. And the path toward that theory is becoming clearer, even as the destination remains out of reach. Most approaches to quantum gravity attempt to quantize gravity, to bring gravity into the quantum mechanical framework that already works for all other forces. Roger Penrose, one of the most distinguished mathematical physicists alive, has for decades argued for the opposite direction. He proposes that gravity modifies quantum mechanics, rather than the other way around. Penrose's argument begins with the quantum measurement problem. A quantum superposition, according to standard quantum mechanics, continues indefinitely until a measurement forces it into one definite outcome. The Schrödinger equation, which governs quantum evolution, is linear and continuous. It never, on its own, produces a definite outcome from a superposition. The transition from superposition to definite result, called wave function collapse, is imposed on top of quantum mechanics as an additional rule that is never derived from within the theory. Most physicists treat this as either a practical approximation or a conceptual issue to be addressed by interpretation, not as a fundamental physical problem requiring new dynamics. Penrose disagrees. He argues that wave function collapse is real, physical, and caused by gravity. The argument runs as follows. A quantum superposition of two different position states for a macroscopic object corresponds, through general relativity, to two different spacetime geometries. The object is in two places at once, meaning spacetime is in a superposition of two different geometrical configurations. Penrose argues that two different spacetime geometries cannot coexist in superposition indefinitely. There is a gravitational energy cost associated with maintaining the superposition, related to the difference between the two geometries. When this gravitational energy exceeds a certain threshold, the superposition spontaneously collapses to one or the other geometry. This collapse is objective, physical, and random. It is not caused by an observer or a measurement apparatus. It happens on its own, driven by gravitational self-energy. Penrose calls this objective reduction. The timescale for collapse depends on the mass of the object and the separation between the two superposed positions. For small particles, quantum superpositions persist for long times. For macroscopic objects, the collapse is essentially instantaneous, which is why we never see cats in superposition. This proposal is testable. The Felix proposal and related experiments, including the MAQRO experiment being developed for a space platform, aim to place objects of increasing mass in superpositions and measure the decoherence timescale. If Penrose is right, the superposition should collapse on a specific timescale set by the gravitational energy difference between the two geometries. If standard quantum mechanics is right, in the absence of environmental noise, superpositions can persist much longer. The Penrose approach is a minority view in the physics community. Most researchers find the idea that quantum mechanics is modified by gravity harder to accept than the alternative. Quantum mechanics has been tested with extraordinary precision, and no deviation from linearity has ever been observed. Modifying it requires an extreme departure from a framework that works perfectly in every experiment conducted so far. But the minority position is scientifically serious. Penrose is not proposing untestable metaphysics. He is proposing a specific physical mechanism that makes concrete experimental predictions, distinguishing his view from standard quantum mechanics. Whether the experiments will confirm or refute it, no one yet knows. The deeper point Penrose raises is worth holding on to, regardless of whether his specific proposal survives. The relationship between quantum mechanics and gravity may not be purely about quantizing gravity. It may also involve gravity-modifying quantum mechanics in ways that resolve its foundational puzzles. The direction of influence between the two frameworks is an open question, and the answer may surprise everyone. The last decade in quantum gravity has been unusually productive, not in the sense of delivering a complete theory, but in the sense of establishing precise new results that constrain what a complete theory must look like. The island formula and the page curve derivation represent the most significant technical advance. Starting around 2019, researchers including Ahmed Almheri, Netta Engelhardt, and Jeffrey Pennington showed that the page curve, the expected evolution of Hawking radiation's entanglement entropy, if information is conserved, could be derived from a gravitational path integral calculation using a concept called the island rule. In specific models of quantum gravity coupled to matter, the entropy of the Hawking radiation follows the page curve exactly. The derivation does not require postulating new physics beyond standard quantum gravity assumptions. Information appears to be conserved, emerging from gravitational path integral contributions that include regions of spacetime inside the black hole, called islands. The island formula has been verified in several model quantum gravity systems, including the Jacquiot-Teitelbaum two-dimensional gravity model, which serves as a tractable laboratory for quantum gravity ideas. The results support the view that unitarity, the quantum mechanical principle of information conservation, holds in quantum gravity, and that the Hawking radiation eventually encodes all infalling information. The mechanism by which this happens remains partially mysterious. The islands provide a geometric encoding of the information in the path integral, but a fully explicit, step-by-step description of how an observer outside the black hole could in practice decode the information from the radiation remains absent. On the experimental side, the mid-2020s saw continued progress in quantum sensing technology. Levitated nanoparticles, tiny glass spheres suspended by laser beams in high vacuum, have achieved increasing levels of quantum control. The technology needed for the gravitational entanglement experiment proposed in 2017 is advancing. Several groups have reported maintaining macroscopic objects in quantum states for duration and at mass scales approaching the experimental requirements. Gravitational wave astronomy has expanded substantially. The number of detected compact object mergers has grown into the hundreds, with joint detections by ground-based interferometers and increasing sensitivity. The Einstein telescope and Cosmic Explorer, planned next-generation detectors with dramatically improved sensitivity, are in advanced planning stages. Their sensitivity will probe post-Newtonian corrections to general relativity at levels that may begin to reveal quantum corrections if they are large enough. On the theoretical side, the program connecting quantum error correction, holography, and the emergence of space-time from entanglement has continued to deepen. New connections between replica wormholes in the gravitational path integral and the page curve calculation have been established, providing a more microscopic understanding of how unitarity is maintained. The holographic entanglement entropy formula of Ryu and Takayanagi has been extended and placed on increasingly firm theoretical footing. The field has also seen renewed interest in non-perturbative approaches. Matrix models, which describe quantum gravity as the large number limit of certain quantum mechanical systems involving matrices, have been studied numerically with increasing sophistication. The Sakdev-Yekitaev model, a quantum mechanical system of randomly interacting particles that exhibits behavior characteristic of near-extremal black holes, has become a central testing ground for quantum gravity ideas. What these advances share is a common theme. Gravity and quantum information are the same physics described in different languages. The translation between them is being worked out, piece by piece, with increasing precision. A complete quantum gravity theory may not arrive as a single dramatic breakthrough. It may crystallize from the accumulation of precise results connecting space-time geometry to quantum information structure, until the full picture becomes unmistakable. You have now traveled from the ordinary pull you felt on your body at the beginning of this journey, all the way to the deepest open questions in theoretical physics. Take stock of where we have arrived. Gravity at large scales is understood with extraordinary precision. General relativity remains one of the greatest intellectual achievements in human history. Its predictions have been confirmed by a century of experiments, from the bending of light around massive objects to the detection of gravitational waves from colliding black holes a billion light-years away. Every satellite in orbit, every navigation system on your phone, operates with corrections drawn directly from Einstein's equations. At the smallest scales, quantum mechanics governs everything with equal precision. The standard model of particle physics, built on quantum field theory, predicts the behavior of electrons, quarks, photons, and nuclear forces with accuracy. That is, in some cases, the finest precision ever achieved by any scientific theory. No experiment has ever found a violation of quantum mechanics. Between these two frameworks lies a gap, a deep, genuine, scientifically serious gap. At the Planck scale, roughly 10 to the negative 35 meters, where both theories are simultaneously relevant, they are mutually inconsistent. Quantum gravity is the framework that must bridge them, and it does not yet exist in complete form. What is known with confidence about quantum gravity? Gravity must involve a quantized force carrier, almost certainly the graviton, though detecting it is probably permanently beyond experimental reach. The black hole entropy formula, connecting information content to surface area, is accepted as correct. Hawking radiation is a theoretically robust prediction that has been validated indirectly through analog gravity systems. The AD/CFT correspondence is a proven mathematical result demonstrating that quantum gravity in one setting is equivalent to a quantum field theory without gravity in another. Information is very likely conserved in black hole evaporation, based on the page curve derivations of recent years. What remains genuinely open? No confirmed quantum gravity theory exists. String theory is mathematically rich, internally consistent, predicts the graviton naturally, but has made no unique confirmed experimental prediction. Loop quantum gravity provides a consistent quantization of spacetime geometry and predicts a discrete structure at the Planck scale, but has not been experimentally confirmed. Whether spacetime is continuous or discrete is unknown. Whether extra dimensions exist is unknown. Whether time is fundamental or emergent is unknown. The cosmological constant problem, the 120 order of magnitude discrepancy between predicted and observed vacuum energy, remains fully unresolved. What is coming? The tabletop gravitational entanglement experiments, if successful in the next 1 to 2 decades, will confirm whether gravity is quantum mechanical at all. Next-generation gravitational wave detectors will probe general relativity with far greater precision. Advances in quantum information theory will continue to sharpen the translation between space-time geometry and quantum information structure. Astronomical observations of the cosmic microwave background will constrain quantum gravity scenarios for the early universe. The question of what gravity is made of has driven physics for centuries. Newton gave us the mathematics of gravity without its mechanism. Einstein gave us the geometry of space-time and showed that gravity is shape. Quantum mechanics gave us force carriers and the particle nature of all other forces. The final answer, the framework that explains what shape itself is made of at the deepest level, what space-time looks like when you zoom further in than Einstein ever could, what gravity is in the language of quantum reality, remains ahead. The frontier is not receding, it is coming into focus. The questions are sharper now than they have ever been. The tools are more precise. The mathematical connections between apparently unrelated fields are revealing a hidden coherence that grows clearer every year. Gravity may be woven from quantum entanglement. Time may be a collective illusion arising from correlations in a fundamentally static universe. Space itself may be a hologram, a projection of information living on a surface you can never see from inside. These are not metaphors. They are, with various degrees of confidence, the directions toward which the best evidence currently points. The universe you are sitting in, held to this planet by a force that has never been fully explained, is stranger and deeper than any description physics has yet produced. And the next step toward understanding it is being worked out right now, in laboratories, on whiteboards, in lines of code, running on computers, modeling spin foams, and causal sets and tensor networks, and entangled masses hovering in laser traps. The answer, when it arrives, will change what we mean by real.